Okay, Notes 2.6, Nonlinear Inequalities. So this is going to be the last section of Chapter 2, and we're going to start out by going back to polynomial inequalities, the ones that don't have any discontinuity, the smooth rounded curves, but inequalities mean that we're going to be comparing them. So rather than just values, we're going to have intervals, which are our solutions. So let's read through this first paragraph and get started to kind of understand what we're going to do. So to determine the intervals on which a polynomial inequality is positive or negative, excuse me, we have to remember that the locations where polynomial functions change sign are at the zeros of the function. So if you think back to the intermediate value theorem, that was a procedure that let us determine that when we went along the x-axis among the consecutive integers, if we had a sign change in our y values, that meant we had a zero of the function or an x-intercept. So we're still going to locate those zeros so that we can look for the sign changes. By finding those zeros, we can identify intervals where we have either all positive or all negative. Then we're going to use a sign chart to denote the positive and negative intervals, and that's just going to consist of a number line. That's going to be pretty easy. Don't forget to get 0 on one side of the inequality before you set up the intervals. So what we want to do when we compare positives to negatives, that's putting them up against 0. If it's greater than 0, it's positive. If it's less than 0, it's negative. So we want to always be comparing to 0 when we set up our intervals. Let's look at example 1. So we have this quadratic, x squared minus 8x plus 16 is less than or equal to 1. So the first thing we want to do is subtract the 1 and have x squared minus 8x plus 15 less than or equal to 0. So now that we're comparing it to 0, on the left, we see that we want this left-hand side to be less than or equal to 0, which would be negative values. So we want x values that would make the result less than or equal to 0. So to find those zeros or those critical points, we're going to factor this one. Things that multiply to give me 15 that add up to give me negative 8 are going to be negative 5 and negative 3. So I'm going to set each of those equal to 0. And x will be 5 and x will be 3. So as I look at this now, these are my critical values. So the number line that we're going to use is like our sign chart. So I have 3 and I have 5 as my zeros. And because it says less than or equal to 0, those will be included in my solution. So as you can see now, we have the number line divided up into 3 sections. And what we want to do is test each section. So I want to test a value that is less than 3. I'm going to test 0. I'm going to test 4 between 3 and 5. Whoops. And I'm going to test 6, which is greater than 5. So again, I have these critical values, which I place on the number line. And then I'm going to use that to look at the different intervals along the x-axis where my function is positive or negative, and we are looking for negative results. So look at, as we take 0, we're going to go back and look right in here when we plug in these test values. So if I do 0 minus 5, I get a negative. 0 minus 3 is a negative. So a negative times a negative gives me a positive in that region or on that interval. Let's test 4. 4 minus 5 gives me a negative. 4 minus 3 gives me a positive. So a negative times a positive is a negative. And then we're going to test 6. 6 minus 5 is positive, and 6 minus 3 is positive. So a positive times a positive is a positive. Okay, now that we have defined each interval and what kind of signs we have, our solution, remember, wanted negative values. So these were all of our testing values. And what we discovered is if we want negatives, that's going to be in between 3 and 5, including 3 and 5. So the solution for number 1 would be from 3 to 5, including those, so we'd want to make sure we had brackets. Now, one thing you can do graphically to check this is you could go to your calculator and plug this in to y1, and when you do, you're going to see this happen. You're going to see a parabola that's opening upward that actually goes down through 3 and back up through 5. And so what you notice is that it is negative everywhere from 3 to 5. So that really confirms that we have the correct interval for our solution. Okay, let's look at example 2. 2x squared minus x minus 4 is greater than 2. So we're going to set this equal to 0, or subtract the 2 from both sides. So 2x squared minus x, and as I subtract 2, negative 4 minus 2 is negative 6, greater than 0. This factors. So, but before we look at that, I'm sorry, we want this to be greater than 0. So when we look at our interval on the x-axis, we want positives. So as we factor it now, factors that multiply to give me negative 12 and add up to give me negative 1 are negative 4 and 3. So I'm going to do x minus 4, x plus 3, divide by 2. So my factors are x minus 2 and 2x plus 3 being greater than 0. So my critical values are 2 and negative 3/2. So these are where the function would equal 0. These are my critical values. So I'm going to set up my number line and look at each interval and test these values. So I have negative 3/2 and I have 2. I have open circles at both of these values because they cannot equal 0 according to my equation. Right here I have that it's just greater than 0. So now let's test. I'm going to pick negative 2 as a value to test. I'm going to pick 0 to test, and I'm going to pick 3 to test. And again, I just want to know if I have positives or negatives, and we are looking for positives. So if I plug negative 2 into these two binomials and multiply them together, negative 2 minus 2 will give me a negative 4, and 2 times negative 2 plus 3 will give me a negative 1. So two negatives are going to make a positive. If I plug 0 in, 0 minus 2 is a negative, and 2 times 0 plus 3 is a positive 3. So I would get a negative times a positive, which is negative. And if I plug 3 in, I'll get 3 minus 2 is positive 1, and 2 times 3 is 6, plus 3 is 9, so I would get another positive. So in this case, my solutions are going to be on the intervals of my number line where I have positive values. So to write that in interval notation, my solution would be from negative infinity up to, but not including negative 3/2, and from 2, not including 2, to infinity. And so as you look at a graph, again, if you wanted to confirm this, you're going to see a quadratic that is opening up. It's crossing through negative 3/2 and 2. And we want where it's positive, and that's going to happen on those intervals above the x-axis. Okay, let's look at example 3. We have 4 different equations, and I want you to look at A and B. Notice that A and B are actually almost identical. These are kind of special cases. X squared plus 5x plus 8 is less than 0, and x squared plus 5x plus 8 is greater than or equal to 0. So there's going to be something special that we're going to look at with these. Let's start with A. So I'm going to factor A. Actually, I'm not. There are no two things that multiply to give me 8 that add up to give me 5. So we still have to solve it. We still are looking for negative values. We want it less than 0. So we're going to use the quadratic formula. So x will equal a negative 5 plus or minus the square root of 5 squared minus 4 times 1 times 8 all over 2 times 1. So when I look at this, I get negative 5 plus or minus. Now inside, I would get 25 minus 32. That's a negative 7 over 2. So if there was a way to plot this on the real number line, we don't have it. This is an imaginary number. So there are no critical values. And that is mostly because that is imaginary. And so we have no real values. Oops, I can't spell. Okay, so what that really means is this is never true. And there's no solution. So if we even think about this logically, there's nothing I could ever plug in for x that would ultimately give me a negative value on the left-hand side. Okay, so as we note that, let's move to b, which as we said is really the same equation, but now it's greater than or equal to 0. So what we know to be true, we've already done the math on that, so we know that x is going to equal positive or negative infinity, or sorry, x is going to equal negative 5, sorry, hold on, plus or minus the square root of negative 7 all over 2. So if there are no critical values, again, these are just our critical values. Well, what does this mean then? If we think about this, where will it be greater than or equal to 0? Any number in the real number system that I plug in would make this true, and you can test some values. There are no critical values, so just plug any number in. You can plug in 2, you can plug in negative 6. Any number that you plug in will make this true. So in this case, my interval is everything. This is always going to be true. So my solution is negative infinity to infinity. It is everything. Okay, let's look at C and D. So again, notice with C and D, they are the exact same polynomial. One says it's greater than 0, and the other one says it's less than or equal to 0. So let's see what's special about these. I can factor x squared minus 10x plus 25 to x minus 5 squared. That's a perfect trinomial square, being greater than 0. So this means I'm looking for a positive. I want to know where this is positive. Well, the critical value is going to be x minus 5 equaling 0, which is 5. So here I have 5. Now it has to be strictly greater than 0, so I have an open circle at 5. So I'm going to test a value below 5 and above 5. I'm going to test 0, and I'm going to test 10. And I'll plug them in. So if I have 0 minus 5, that's going to be a negative times a negative because there are two of them, x minus 5 and x minus 5. So a negative times a negative gives me a positive. And then if I plug in 10, 10 minus 5 is a positive. A positive times a positive is also positive. So what we have is something that has a solution everywhere except 5. Every value. Sorry, every value is a solution except for 5. So in interval notation, that looks like this. My solution is from negative infinity to positive 5, and then from 5 to infinity. So we're just not including the 5. Okay, so that's a little different. Letter D. Again, this is going to factor to x minus 5 all squared less than or equal to 0. So we are still looking for, or we're still having the same critical value of 5, but now I want it to be negative. So my critical value is when I set x minus 5 equal to 0, and again, x is 5. So as I graph this, it can equal 5 because it's less than or equal to 5, and I'm looking for a negative. So I'm going to test 0 again and 10 again, but I already knew that when I plugged in 0, 2 negatives made a positive, and when I plugged in 10, 2 positives made a positive. But I'm looking for negatives. So the only solution to this is the number 5. That's the only solution that worked. So these 4, still all of the same concepts apply. The solutions to them are just a little bit different. We don't see them very often, but they are out there and we just want to be ready for them. Okay, rational inequalities. So now we're leaving the polynomials to rationals, which have denominators. And as we know with denominators, we have to be careful of when they're undefined, or when they're 0, which makes our function undefined. So rational functions also change signs. They can change signs at the zeros or at points of discontinuity. So if we have a hole in the graph, that can also change it. So when finding values for the intervals, we must include zeros of both the numerator and the denominator. That's going to be really important here in a second. With these, be sure to write the inequality in general form with a single rational expression on the left and a 0 on the right. So once again, we're putting it up against 0. Now what we did in 2.5 when we solved rational equalities was we would multiply everything by the least common multiple. So as we would get started on that, if we treated this like an equality, it's already put up against 0 again, and I want it to be positive over here, I would multiply everything by x plus 2. So as I do that, when I multiply to the first term, x plus 2 cancels, and I have 3x plus 4, minus, when I multiply it to the 5, I get 5 times x plus 2 is greater than or equal to 0. Now what happens is it now looks like a regular polynomial. I have no more denominator. So that's a problem because in our original equation, we had a place where the function was undefined. We had a restriction on our domain, and we have to remember that. In the beginning, x cannot equal -2. That is a restriction. Even though it cancels when we multiply through by the least common multiple, that is a restriction on our domain. So when we graph this line, we already have a critical value at -2. So we want to make sure that we put -2 on there. And it's an open circle for sure because it cannot equal -2. Now we're going to go ahead and continue to solve this polynomial that we now have. 3x plus 4 minus 5x minus 10 is greater than or equal to 0. 3x minus 5x is -2x. 4 minus 10 is -6, greater than or equal to 0. I'm going to add 6, so -2x is greater than or equal to +6. And when I divide by -2, I get x is now less than or equal to negative 3. Don't forget to reverse the inequality when you divide by a negative. So my other critical value is here at negative 3. And it says it can equal negative 3. And it was not a problem in our domain, so we can include it. Okay, so now as I divide this up into sections, a number that's less than negative 3, I'm going to pick negative 4. Between negative 2 and negative 3, I don't have much choice. I'm going to pick negative 2.5. And then greater than negative 2, I'm just going to pick 0. And we're going to test these values. So again, I'm looking for positives. So I'm going to plug in, it's important that we plug these test values into the original. We're not going to be plugging in a negative 2, so we're safe to plug into the original equation. So if I plug in negative 4, I would have 3 times negative 4 plus 4 over negative 4 plus 2 minus 5. If I evaluate that, I get a negative 8 over a negative 2, which is 4 minus 5, or negative 1, but essentially it's the negative that I'm concerned with. So I get a negative in this interval. Then I'm going to plug in negative 2.5. 3 times negative 2.5 plus 4 over negative 2.5 plus 2 minus 5. When I look at that, that's actually going to give me a positive value. I don't have that calculated, but I know that that's going to lead me to a positive. So in this interval from negative 3 to negative 2, I'm going to get positive values. And so then I have, and I think that turns out to be a 7. If I'm looking at my notes right, I've done this before. I think that's a 7. So 7 minus 5 is a positive 2. And then the last one, if I plug in 0, 3 times 0 plus 4 over 0 plus 2 minus 5, that gives me 2 minus 5. 4 divided by 2 is 2, minus 5 is a negative 3. So this interval is negative. Since I'm looking for a positive, my solution interval is right here from negative 3 up to, but not including negative 2. So here's my solution, including negative 3 up to, not including negative 2. Okay. So one last question. We're going to do an application problem. All right, a carpenter is making tables. The tables have rectangular tops, so I'm going to make a rectangle. Hopefully I can. Okay, well, okay, that's pretty rectangular for me. The perimeter is 20 feet, and the area of at least 24 square feet. So down here, the area is at least 24 square feet. That means it can be 24 feet exactly, or it can be more than 24 feet. So area is greater than or equal to 24. Write and solve an inequality that can be used to determine the possible lengths to which the table can be made. Well, I know that area is length times width, and I want that to be greater than or equal to 24. I also know that perimeter is 2 times the length plus 2 times the width. That's equal to 20. So if I reduce that down and divide out a 2 from everything, I have length plus width equal to 20. And so they want to determine possible lengths, which is my L. And they want an inequality, which is this one over here on the left. So I'm going to replace, oh, and I totally messed this up, guys. Oops, sorry. This is 10, not 20. Great. Okay. Length plus width is 10. Sorry about that. Okay, so if I am determining lengths, I need an L. Well, L in terms of W is 10 minus I'm sorry. I want the width in terms of length so that I can plug that in. So width is going to equal 10 minus the length. So if I'm looking for everything in length, I want to replace W with the value of W in terms of length. And I want to go to the inequality to do that. So length times W, which is 10 minus L, is greater than or equal to 24. And so now we have a polynomial that we're going to solve. So we're going to distribute 10L minus L squared is greater than or equal to 24. So then I'm going to move over the L squared and the 10L by adding. So 0 is greater than or equal to L squared minus 10L plus 24. And this factors. Oh, one more thing right when we're here. We want 0 to be greater. So when I do my critical values and set up my number line, I'm going to look for negative intervals, negative results, or 0, negative or 0. So this does factor. I can write this as L minus 6 and L minus 4. So I'm going to set up this number line, and L would be 6, L would equal 4 as my critical value. So here's 4, and it could equal 4. Here's 6, and it could equal 6. So the values that I'm going to test 0, 5, and 7. Again, looking for negatives. So if I were to plug 0 into L minus 6 times L minus 4, I would get 2 negatives, and that would be a positive. If I were to plug in 5, I would get 1 negative and 1 positive, so that interval is negative. And when I plug in 7, I would get 2 positives. So as I tested these values, I can see that the interval that is negative is from 4 to 6, including those values. So if it says to write and solve an inequality that can be used to determine the possible lengths to which the tables can be made, the solution is lengths between 4 I don't know what I'm pressing here, and 6 feet. In interval notation, it looks something like this. Okay, so that's an application that we can use these inequalities for as well. All right, that concludes 2.6, and you have reached the end of Chapter 2.